The Nyquist stability criteria is just another stability criteria, as you can see. What is the stability criteria for the time domain system or the S domain system? Is the same concept we are using here. When the system is stable, we know that the poles of the closed loop system should be the closed loop transfer functions. All poles should be on the LHS of the S plane. Okay. When the system is stable, when the system is unstable, any one of the pole may be lying on the RHS side of the S plane. Okay, so that's why the part of the S plane which we are interested here is the right hand side of the complex S plane. Okay, the entire right hand side, or you can say starting from the imaginary axis to the infinite to the right hand side. Okay. The mapping which we have discussed yesterday. Okay, any one of the function. Okay, like GH function has a definition of S plus 1.5. When any we put the different values for S here, we get different values for GH or the open loop transfer function. That is called as the mapping. Like this here you can see. The definition of GH plane is 2. S plus 1.5 and this point is mapped here. Similarly, one more point, when we put into the GH plane, the GH function, it can be mapped somewhere here. If we follow those, if we follow the different values of S in a closed path, either in the clockwise direction or in the anti-clockwise direction, we can see the mapping also will be like a clockwise or anti-clockwise direction. Here in this case, we have considered a system equation having two zeros. One zero is inside the closed path and one zero is outside the closed path. I will show you one more demonstration like the one we have seen yesterday. This is S plane for the transfer function S divided by S square 6S plus 18. Okay. And this plane is GH plane. Here it is called as the W plane. Okay. The definition of GH is S by S square plus 6S plus 18. Okay. Now what we will do, this is the point, or we can say a contour, which will be encircling around is 0. So here you can see the change it obtained in the W plane. It is also an encirclement around the origin. Okay. When the 0 is encircled in the S plane, we can also get the encirclement around origin in W plane. Keep that in mind. Even though this 0 is at origin, okay, irrespective of its position, when any 0 is encircled, we get the encirclement around origin. Okay. Follow the directions now. Okay. In the S plane, I am following clockwise direction of the contour or the closed path. You can see in the W plane also we can get the clockwise movement. Okay. When the clockwise movement is there, the angle is measured in negative. Okay. So for one complete circle, we get the one complete encirclement around origin in W plane. Okay. So that's why the total change in argument or the total change in angle becomes 2 pi. Okay. Similarly, let's consider a closed path without consisting or without encircling around any of the poles or the zeros. Okay. Let's consider this is the path. Now you observe the W plane. Okay. The total change in argument here is from this moment to this and again back to this position. So that makes total change in the angle as 0. Okay, because there is no encirclement around origin. When any one of the poles or 0 is not encircled in the S plane. Okay. Now we'll consider one more example when any one of the pole is encircled. Keep that in mind. We are moving in the clockwise direction around the pole. In the W plane, you can see we also got the encirclement around origin. We also got the encirclement around origin. Now verify the angle. So when it is a one complete encirclement, means the 2 pi will be the angle, and the direction in the S plane I am following clockwise direction. In the W plane, you can see it follows anti-clockwise direction. Okay. So that's why the angle will be positive this time. So the angle will be 2 pi. The change in the angle will be 2 pi. Okay. Similarly, we'll consider one more case here, the fourth case. If I encircle around the two poles, okay, see what is happening in the W plane. One complete encirclement in the S plane results into the 2 times encirclement in the W plane. Okay. 1 and 2 is true. Okay. Now follow the respective direction. I am moving in the clockwise direction, encircling around two poles. There you can see the encirclement around origin in the W plane is happening in the anti-clockwise direction. Okay. When I have encircled one pole, the total change in angle was 2 pi. Okay. When I am encircling two poles, or the closed path consists of two poles inside it, here you can get the 2 times encirclement about origin. So the total angle becomes, the change in angle becomes 4 pi. Okay. So that you can see here, if total number of zeros of the function g of s h of s is z, okay, the number of zeros of g of s h of s is z, and s is varied along a closed path, okay, consisting this number of zeros inside that path, we get the total change in argument in w plane or gh plane as minus 2 pi z. Okay. When 0 is encirclement, when the encirclement is around 0, we get the clockwise movement in W. Similarly, if P is the total number of poles present in the count, that particular contour, then the movement in the W plane or the GH plane is anti-clockwise. Okay. So if it is one complete encirclement will result into the one complete encirclement about origin in GH plane. If it is 2, this will be minus 4 pi. If, as we have seen, the poles are 2 in our last case, the total change in angle was 4 pi. So, considering this particular situation, okay, the principle of argument has come up with this formula. The change in argument is equals to 2 pi times the subtraction or the difference between total number of poles minus total number of zeros present in that specified region. Okay, keep that in. Specified region is important. Z are the zeros present in the specified region. P is the number of poles of the complex function in the specified region. Okay. Always keep in mind the specified region plays important role here. Okay. Now let's consider one more thing you can observe here. This is the change in angle, total number of poles, total number of zeros present in the specified region. Now among these three quantities, any two will be given and third can be directly calculated. Okay. So the same thing is here. You can see this is the given S plane contour and this is the GH plane map. Here you can see one pole is present inside the contour where the contour is actually following the clockwise direction, and the mapping in the GH plane is resulted into a clockwise direction. Okay, in the clockwise direction. How many times? one single time. Okay. So the change in argument is minus 2 pi because the clockwise direction is there. Put the total number of poles present in the specified region as 1 into the formula, and you will get the total number of zeros present in this particular case, in this region. Okay. This value of z was not earlier given. This was the position of pole was given, and its mapping in the GH plane was given, okay, or has been calculated, we can say. And using those two quantities, we have obtained the third quantity, that is the total number of z present in the specific region in the S. This is very important. Similarly, when two poles are there and the contour is clockwise in the S plane, what it should basically get, the clockwise or the anti-clockwise rotation. So here you can see its mapping in the GH plane is given in anti-clockwise direction, encircling around origin one single time. Okay. When it is anti-clockwise direction, the angle will be positive, so it is 2 pi is equals to 2 pi in bracket the total number of poles present in the specified region equals to 2 minus z. Z is unknown here. Okay, solving this, we got z is equals to 1. That means in this particular specific region, one z is also there. Hence 1 0 is also there. So using this particular mapping, you can calculate how many total number of zeros and poles can be available or can be encircled in this specific region. Here in this case, let's consider we are given with two poles outside the contour, and its mapping is actually also happen to be is not encircling around origin. Okay, means the total change in angle will be from this to this and again back to this position. That will be the maximum change it can achieve. So it will the total change in angle will be 0. Okay, so 0 is equals to 2 pi in bracket total number of poles present in this specific region is again 0. So the zeros present, or the total number of zeros present in the specific region, or it is called as the contour, is 0. Now here we'll consider one more case when in the S plane, in the contour which is moving clockwise direction contains two poles. Okay. And in the W plane or the GH plane, we can get encirclement around origin in the anti-clockwise direction two times. Okay. So the total change in argument will be 4 pi. Total number of poles present in the specific region is 2. So the zeros present here is 0. There is no 0 present in this particular case. Now, why this is important? I'll tell you. This is very important. Why? The calculation of Z is obtained using this mapping. Because the important thing is the difference between GH and 1 plus GH. Okay. Now, when we calculate the stability of the closed loop system, we consider a general closed loop transfer function as G divided by 1 plus GH, okay, where the GH is open loop transfer function, okay, and 1 plus GH, that is the denominator of the transfer function, is called as, when it is equated to 0, it is called as the characteristics equation. Let's consider the GH or the open loop transfer function is defined as the numerator polynomial and the denominator polynomial. This polynomial, when we solve or equate it to 0, we get the zeros. When it is equated to 0, we get the poles. These are the zeros and poles of GH or the open loop transfer function. Okay. Now, using this definition of open loop transfer function, let's calculate the characteristics equation. It is 1 plus GH. That will be 1 plus this transfer function. Okay. Now, it has the poles. If we simplify it, this poles will be here. Poles plus numerator, that is zeros of the open loop transfer function, and in the denominator we are left with only poles of the open loop transfer function. Okay, that is what we have to observe here. Simplifying the numerator, we'll get some polynomial. Simplifying the numerator, we get the simplifying the numerator, we get the zeros, and simplifying the denominator, we got the poles. Now observe, this is the characteristics equations, poles and zeros, and these are the open loop transfer functions, poles and zeros. Now here you can see the zeros polynomial and zeros polynomial here are different. Okay, but the poles of the open loop transfer function and poles of the closed loop transfer function are same. Okay, that's why this z, or the total number of zeros of the closed loop or the characteristics equation, we cannot calculate directly. Okay, that's why we use this mapping to calculate the total number of zeros. Okay, because the stability will be like the poles of the transfer function should all lie in the LHS of the S-plane. This will be the area for stability. The poles of the total transfer function should lie in the S-planes or the LHS of the S-plane. Okay, what about this instability? For instability, any one of the pole may be lying on the RHS side. Okay. Now, what about the poles of the open loop transfer function? Here you can see the poles of open loop transfer function is obtained when I equate the characteristics equation to 0. Okay, and this is what the characteristics equation is a polynomial having the is a ratio of numerator polynomial and the denominator polynomial. So the numerator polynomial equates to 0, we got the zeros, and when we equate the denominator polynomial equals to 0, we got the poles. One thing you have to observe, the poles are same. Okay, open loop transfer function and the characteristics equation both have the same poles. Here you can see GH and 1 plus GH equals to 0, that is the characteristic equation, have the same poles but different zeros. Okay. The zeros of open loop transfer, the zeros of closed loop transfer function obtained through the characteristics equation are the roots of it. Okay. So for the stable system, all the zeros of the G1 plus GH equals to 0 should lie on the LHS. Okay. And when the system to be unstable, any one of the pole of the closed loop transfer function or the zero of the characteristics equation may be lying on the RHS plane. Okay. So that's why the Nyquist criteria is actually gives you idea, or it helps to identify the presence of zeros of the characteristics equation which is present in the RHS of the S plane. Okay. In the RHS of the S plane with zeros of 1 plus GH. Keep that in. Instead, we are identifying here for the closed loop system. For the closed loop system. And what region or the encirclement we are asking about? The RHS of the S plane. The entire half S plane. Like this. The path along which the S will be varied is completely S plane. The half of the S plane. This imaginary part. And the negative imaginary axis, the positive imaginary axis, and all the this RHS of the S plane. Okay. So how do we represent, or how do we put the mathematical expression for this S plane? It you can consider as a semicircle with the infinite radius. A semicircle with infinite radius. Okay. Limit r tends to infinity, r e to the power j theta, because it is the complex function. Now let's consider what is the value of pole, or the definition of pole is when any one of the pole is present on the origin. The value, the pole is the value of pole makes the system, the value of transfer function is infinite, and when any one of the zero, the value of 0 is called as the value for the transfer function which makes its value to 0. So in many of the books, you will see this entire S-plane or the Nyquist contour. You can see the half, the RHS of the S-plane. In some books, it is represented like this. Now, what is it? At the origin, there is no encirclement, or this particular point is not directly connected like this. The reason is when any one of the zero presents here, what will happen? The magnitude will be 0. Okay, so that's why when any one of the pole will be encircled, any one of the zeros will be encircled, this particular magnitude will be 0. So that's why this is taken as the limit r tends to 0, and the outer limit for the complete half RHS is taken as limit r tends to infinity, e j theta. Okay. Now the mapping in the GH plane is done. Okay. From the mapping, we can calculate the change in the argument. Now using this, okay, up till now we have considered one specific plane as GH plane. Okay, the change in argument in the GH plane is given by 2 pi in bracket p minus z, where p is total number of poles present in the specified region and the total number of zeros present in the specified region. Okay. And that specified region we have just considered as the RHS. Okay, the RHS of S plane. Okay. Keep that in mind. We have taken into consideration the open loop transfer function GH. Okay, the above procedure calculates the total number of roots of G of S, H of S, and not for the 1 plus G of S, H of S. Now, why so? But we are interested to find the stability of closed loop system. Okay, so GH and 1 plus GH has this one difference, that is 1 is to be added in each and every complex value. Okay. Now, what will happen because of that? When we consider the characteristics equation for the closed loop system, the origin will be also shifted. Okay, that's why when we consider GH, will we are identifying the encirclements around origin, that is 0, 0, and when we consider characteristics equation or the stability of the closed loop system, we consider minus 1, 0 as the critical point in this same plane. Okay, we consider everything in the GH plane, but we are identifying for the closed loop system. That's why we'll consider the minus 1, 0 along which the encirclements are obtained or not. Okay, that is the same thing. Okay. Change in argument, okay, where the origin of minus 1, 0. The origin is shifted to minus 1, 0 in the GH plane. So the change in angle or the change in argument is again the same. Formula is same, equals to 2 pi in bracket p plus minus z plus. That is nothing but the p plus is the number of poles with the real part, and z plus is the number of zeros with the positive real part. Okay. For the stable system, tell me what is important. For the stable system, zeros of the closed loop transfer, zeros of the characteristics equation. Okay, zeros of the characteristics equation should be lying on the RHS or LHS. They should be lying in the LHS side, not on the RHS. But the the contour we are considering is the RHS side. So the Z plus, the number for the Z plus for the stable control system should be 0. When Z is equals to 0, when Z is equals to 0, okay, the formula will be this. Okay, one point we have left here. The change in angle is multiple of 2 pi. Okay, if I divide it with 2 pi, I will get the total number of encirclements, and the encirclements are positive in the clockwise direction, in the negative from the anti-clockwise direction, and the encirclements are positive in anti-clockwise direction. So the total number of encirclements, if it is given, and for the stable system, the total number of zeros should be 0. Okay, So we get the total number of encirclements equal to the total number of poles present in the specified region. The specified region is RHS of the S-plane. Okay. If for one case we consider there are no poles of the GH in the RHS of the S-plane, so that will make it stable for the controls for the stable control system. There will not be any encirclement. That means the region we are considering here is the RHS, and if it does not contain in the S plane, if it does not contain any poles or zeros, that means the system is stable. That means it will not make any encirclement in the W plane or the GH plane. Well, let's consider one case here. When we plot the Nyquist plot, the Nyquist plot is actually a kind of polar plot, as polar plot is actually for the variation of frequency from 0 to infinity. Okay, but here in this case, for the Nyquist plot, we consider the variation of frequency from minus infinity to plus infinity. Minus infinity to plus infinity. This is minus infinity to minus 0, then minus 0 to plus 0, plus 0 to plus infinity, and then again for the non-imaginary excess values, it is consists of all RHS plane of the S plane. Now, how do we get the variations from minus J0 to plus J0? That is not so important, but you can directly see here the angle. This point is at what angle? This is 0 angle, this is minus 90 degree, this is minus 180, this is minus 270 or plus 90. So this point is at minus 90 degree, this point is at plus 90 degree. So if any one of the poles is at that particular position, what will happen? We'll get the infinite as the magnitude. That is what we have seen. Let's consider this one example. One pole is at the origin and one is non-zero pole. Okay. Solving this, you can get the initial point as infinite angle minus 90 degree, and the terminating angle or the terminating value for the omega is equals to infinite. We got 0 and minus 80 degree. Okay. This is how it will be at infinite and at 0. Okay, when omega is equals to 0 and when omega is equals to infinity. What happens with the Nyquist plot is it is the extended polar plot actually. So for the all the other frequencies, that is from 0 to infinite in the negative direction, we got the mirror image of the polar plot around the real axis. Okay. So this graph will be like this for the polar. This is half 0 to infinity variation of the omega. We got the polar plot. From minus infinity to plus infinity variation of the frequency, we got the Nyquist plot. Okay, so we got the mirror image. Now what happens here, you can see for omega is equals to 0, positive 0 and minus 0, here you can see these 2 points are supposed to be 1 point only. Okay, we are talking about the GH plane. In the S plane, it is the same point, the origin, but in the GH plane, we got the 2 ends. Okay, so how to connect these 2 ends? Okay, with minus infinity and plus infinity are happen to be coinciding at the origin. So that is only happening because of the pole at the origin. When we consider pole at the origin in the S plane, okay, the variations are from minus 90 degree to plus 90 degree, minus 90 degree to plus 90 degree. So total change in the argument is happens to be pi or the 180 degree. How do we join them? In the clockwise direction. I'll show you. You can note down this particular graph. If there is the type of the system is called as poles present at the origin, the total number of poles present at the origin. When the system is type 0, okay, the change in frequency at 0, omega is equals to 0, is 0. Okay, there is no change will be there. But the type 1 system will be there, the change in argument will be 180 degree. With what magnitude? Infinite. This system is for one type 1 system. Okay, type 1 system is this. Its Nyquist plot is obtained as this. Okay. Now what will happen? For -0 to +0, it will reach through radius of infinite magnitude, and the change in angle is 180 degree. Okay. How many times? 1. If the type of the system is 2, the change in angle will be -2 pi. Okay, that is from -180 degree to +180 degree, or 0 to 360 degree, or 90 to +90 degree, like that, and so on. Okay. Like this, here you can see. Now, what we are interested, if the system is stable or not, that will be obtained because we have to see the encirclement is to be around -1. If it is around -1 or not, we are interested in that point only. Here you can see the system is the closed loop system, or this Nyquist plot is not making any encirclement around -1, 0. Okay, that means we can say the system is stable. So total number of encirclements around -1 is 0. Total number of poles in the RHS side is already 0. Okay. So using these two values, we have solved and calculated the value for total number of zeros present in the RHS side. Okay. This is the system transfer function. Okay. What? Open loop transfer function. Okay. Keep that in. This is open loop transfer function. One pole is at origin, one is non-zero. Okay. But that is on the LHS side. Okay. So we have identified the total number of poles present in the RHS, and from the Nyquist plot we got the total number of encirclements around -1, 0. Both values are 0, so ultimately Z is also 0. So here you can see the closed loop system is stable. Closed loop system is G divided by 1 plus GH. That particular system transfer function is stable. Similarly, here you can see this is S is equals to minus, this is S is equals to minus. All poles are at on the LHS side. Two poles are at origin, and 1, 0 of the open loop transfer function is at again in the LHS side. Now plotting this, here you can see it will be like a graph like this, the polar plot. Okay. Now we will take the mirror image of it. So we'll get the graph like this. Okay. Graph like this. Now when to connect +0 to -0. Okay. That is the important point here. So we have already seen when the type of the system is 2. Okay. The magnitude by which this 2 will be connected is infinite, and the angle by which they will be connecting in clockwise direction will be -2 pi, because the two poles are at the origin. So these 2 points will be connected like this. Okay, let's consider one more example for the open loop transfer function. Okay, g of s, h of s. H of s is 1. Okay, unity feedback system. That's why gh is equals to s plus 0.25 and s square s plus 1 s plus 0.5. This is the open loop transfer function we are given. First, to draw its polar plot, we'll make the s as j omega. That means the frequency response of the open loop transfer function will be replacing s with j omega. Okay. So the polar plot ची starting आपण omega is equals to 0 पासून करतो and termination करतो आपण omega is equals to infinity. ओमेगा इज इक्वल टू 0 पुट केल्यानंतर ओपन लूप ट्रान्सफर फंक्शन so magnitude infinity आणि angle minus 180 degree. So that is the initial point of the polar plot. When omega is equal to infinity, magnitude होतं 0 आणि angle येतो plus 90 degree. Okay, so minus 180 degree to plus 90 degree. This is how it will go. Okay, but you can see the initial guessing will be like this. This is the minus 180 degree angle, and this is plus 90 degree angle. Okay, so how it is going to be, we'll see. When it intersects with the real axis, imaginary part will be 0. By solving this or calculating the imaginary part equals to 0, we got the omega is equals to 0.3536, and the real part is at minus 5.4 when it crosses the imaginary axis. Okay, when it crosses the imaginary axis, okay, the real part is at 0. Okay, so when it crosses the imaginary axis at omega is equals to 0.3536, somewhere like here. And when it crosses the real axis, okay, when it crosses the real axis, when it crosses the imaginary axis, the real part is 0. So real part magnitude happens to be minus 5.4, somewhere here. Okay. So this is the when it crosses the imaginary axis. Sorry, when it crosses the real axis, its magnitude happens to be 5.4. Okay. So when it crosses the negative real axis, that means it is crossing from minus 180 degree and it is jumping from third quadrant to second quadrant, because the initial point at omega is equals to 0, it is at magnitude infinite and angle is minus 180 degree, and terminating point at omega is equals to infinity, its magnitude is 0 and angle is plus 90 degree. So that's why it is transferring from third quadrant to second quadrant and ending on the imaginary axis with angle 90 degree. Okay. This is about the polar plot, this particular region only. Okay. Then the rest of the plot is, to go for the Nyquist plot, we have to find the mirror image of it. So this is how it will look. So it will be originating at 0 minus 0, somewhere that will be infinite magnitude, and the angle will be plus 180 degree because it is the mirror image. Okay, and it is terminating at the origin. Okay, but the angle will be minus 90 degree. It follows the same direction. Okay, as of the polar plot. Now, but the difference is when omega is equals to plus infinity and omega is equals to minus infinity, we got the same point. But when omega is equals to plus 0 and minus 0, here you can see basically this is the one single point, but we got the two ends on the polar plot or the Nyquist plot. Now to connect them, you already know in the clockwise direction, you will get this is the type 2 system. So we have to connect them by minus 2 pi angle with the infinite as the magnitude. Okay, this is how the polar plot will look like this, and the Nyquist plot will look like this. The mirror image connecting all the ends. So here you can see the total number of encirclements around minus 1. How many? This is the 1. This is 2. In what direction? Clockwise direction. The clockwise directions are there. Okay. Twice the clockwise direction. The clockwise direction is negative. Okay. Then how many poles are present in the RHS side? Here you can see this is the open loop transfer function. The poles of open loop transfer function, none. Okay. So the no poles with the real part or the positive real part or in the RHS side. So by the definition, n is equals to p minus z. We got n is equals to minus 2. That is total number of encirclement in the clockwise direction. That's minus 2. Total number of poles present in the RHS side 0. So we got z is equals to 2. Z is equals to 2. Z is equals to 2 means its significance is there are number of roads having the positive real parts are 2. Now, what are these roots we are talking about? The zeros of characteristics equation. Zeros of characteristics equation. The zeros of characteristics equations, out of them, two are on the RHS side. This is the open loop transfer function. Okay, if I make if I write it as 1 plus here, okay, this will become the characteristics equation. Okay, the zeros of the characteristics equation here in this case are obtained as, that number will be something different, but out of those, all poles, two number of poles of the open loop transfer function, or two number of zeros of the characteristics equations are on the RHS side. That's why the closed loop system is unstable. That's why we can say the closed loop system is unstable, because the zeros of the characteristics equations are happens to be positive or the greater than 0 in the RHS side. This is the one example. Another example here you will see. This is the open loop transfer function we are given. K divided by S in bracket tau S plus 1. Okay. Here you can see one pole is at origin and one pole is at, this is the non-zero pole, but this non-zero pole is in the RHS side. Okay. So this is the type 1 system. Okay. And its polar plot will look like this. When omega is equals to 0, the magnitude will be infinite. Okay. And when omega is equals to infinite, the magnitude will be 0. And here, keep this in mind. In the earlier case and this case, the angles will be completely shifted by 180 degree, because this is the minus real part. So it will start from the plus 90 degree, magnitude infinite. It will end on magnitude 0 and angle minus 180 degree, and its mirror image will look like this. Okay. Now, how to connect this omega is equals to minus 0 and omega is equals to plus 0? This is type 1 system. Okay, so type 1 system will connect these 2 points in clockwise direction with the change in angle by minus pi, or the minus 180 degree, that is in the clockwise direction. Okay, so this point and this point will be connected to each other with the radius of infinite magnitude, and this change in angle is minus 180 degree. Okay. Now here you can see this makes the encirclement around minus 1 comma 0. Okay, how many encirclements are around minus 1 comma 0? 1. Okay, 1. And how many poles are on the RHS side? 1. Okay, total number of encirclements around minus 1 comma 0 is 1. Total number of poles present on the RHS side is also 1. Okay, so here you can see the encirclement is in the clockwise direction. Okay, so that's why that will be minus 1. Okay, so n is equals to minus 1. Total number of poles present in the RHS side is equals to 1. So by the definition, we can calculate n is equals to, by using this formula, n is equals to p minus z. We got z is equals to 2. That means two roots of the characteristics equation, two poles of the two poles of the closed loop transfer functions are on the RHS plane, or the RHS of the S plane. That's why the closed loop system is unstable. That's why the closed loop system is unstable. See, we are given with the open loop transfer function. We have to comment on the stability of closed loop transfer function. So that's why the Nyquist plot plays the important role. Okay, we have the number of poles present on the RHS side of open loop transfer function. From this, we will plot the Nyquist plot. First, we'll plot the polar plot, then we'll do the mirror image and connect the remaining terminals to get the Nyquist plot. We have the number of poles, and from this Nyquist plot we can calculate the number of encirclements in the clockwise and anti-clockwise direction, and using that formula we can calculate this Z. This Z is the total number of zeros of closed loop the total number of zeros of characteristics equation. Characteristics equation is 1 plus gh equals to 0. 1 plus gh equals to 0 is the characteristics equation. Okay. Its roots are nothing but the poles of the closed loop transfer function. So when there are two zeros of the characteristics equation, or the two poles of the closed loop transfer function are on the RHS side, the system is unstable. Which system? The closed loop system. Okay. So here we will end our today's session. Okay. The stability analysis using the Nyquist stability criterion is like this. The encirclement should be around -1, 0 in the anti-clockwise direction. The formula is n is equals to p minus z. Okay. The encirclement is in the clockwise direction. It will be taken as negative. When the encirclement around -1, 0 is in anti-clockwise direction, this will be positive. Poles and zeros are for different thing. Okay. P is the total number of poles present in the RHS plane, of open loop transfer function, and Z is the zeros of the characteristics equation present in the RHS plane. Okay. So using these values, we can calculate we can comment on the stability of closed loop system. Okay. So here we will finish today's lecture. In the next lecture, we'll see few of the examples.